Assalamu alaikum everyone. Once again, now we are going to do almost our final labs, 10 and 11, in which the 10th lab is one of the most important labs uh, in the control system theory. As we already know that we study control system theory in order to control the desired output, but the desired output just does not comes across when you mm, just find the plant of the system and you just implement a controller. You have some parameters and strategies that you really need to look into before thinking about your desired parameter. Once what you already know about the desired parameter as desired output is your rise time, settling time, your percent overshoot, your maximum value of the response, and the peak time. If you know the values based on the experience, and the control designer usually know about these values, we can actually get the desired response. Even though what kind of prompt we have with us, we can conveniently tune our control parameters. So the most fundamental and basic controllers and control design theories available in the literature are PID. P stands for proportional, and I stands for integral, and D stands for derivative controls in order to obtain the desired response. In this lab session 10, we are going to study the three terms PID controller and its effect on the feedback loop response. Also investigate the characteristics of each terms. So what happens actually, each term has their different impact, and before going into the details, I have prepared a very brief document while simulating on the Simulink, so that I can give you the initial idea how to tune the PID controllers parameters to get the desired response. Now you can do the same practice to be master on this, because this is a recursive process. Once you understand the PID tuning, then you have to apply the PID tuning on different system. Remember that on the first order system you have a different tuning concept. On the second order underdamped system you can have a different tuning concept, and similarly for overdamped and so on. So now I'll going through a little theory about it. You know, the controller position is always there, and we have a planned dynamics that we could have for first, second, third on multiple order systems. And then this is the fundamental mathematical form of the PID, where the KP, I'll be showing you later some diagram in the separate document which I've prepared for you. The KP is the proportional gain that actually at this point, when you are the input and the output value from the sensor, subtract in this comparator and multiply by with this gain in order to in order to provide a control action, so that you can produce a desired response. Same is the value with your integral, and same is the value with your derivative control. I before going into the detail, as I told you, it is not easy to teach the PID controls in one lab until or unless you do it by yourself after taking initial knowledge from me. So what you have to do is we will be skimming through this, and then I'll be opening the document which I've prepared for you. KP proportional gain and KI integral gain, and KD represents the derivative gain. You can actually, we can say in subscripts. Okay, so here these are the particular terminologies. That this is the U input. That is actually, if you are using a full-fledged PID controller, then the shape should look like this, like error multiplied by the KP, error integrating and multiply by KI gain, and error differentiating and multiply by KD gain. Don't worry about it, I'll be explaining you very well, I am hopeful. So let's take certain example at the first stage. This is our second order system that we have studied in seventh lab. This could be, you could have certain mass, and by using system identification, or you already know the parameters that are going to use in this second order system. What could be your system input? The force is your system input, and displacement is your system output. and then you have this transfer function, numerator, denominator, and then step plant. You can get this response. For example, you are not satisfied with this output, then there is one way: either you reconstruct this system again, or just use a controller to get the desired response. For example, 0.05 is the final value of the output to the unit step input. It means it should have been towards the 1 unit step, but and the steady state error is of 0.95, quite large indeed. Furthermore, the rise time is about 1 second, and settling time. Let's design a controller that will reduce the rise time, reduce the settling time. So what you have to do, you have to just create a simulating diagram and put this second order function, and then you have to actually tune it. So you can tune it. I'll be teaching you little easy methods of tuning. In that case, there are some derivation which controller you have to. In this case, they have shown that they have only used KP as a controller. Like your error comes in and it multiplies by a factor KP and gives to the plant to change the different values. KP affects the plant in such a way. For example, as I remember, KP actually improves both a steady state and transient characteristics of the response. And similarly, when you have KP plus KD, it specifically focus the transient response of the system. And when you have KI and KP, it actually improves the steady state characteristics of the response. That because these things are on record, you can take it. And similarly, finally, you can, if you want to increase overall response because your transient characteristics were not good, just wait a minute. For example, your transient characteristics were not good, and both your steady state characteristics were not good. In that case, you have to use PID both. So the selection of PID, let me open it and wait a minute, just give me a second. Okay, for example, if you are opening it and you are having, for example, you are having um, k actually, if you the k means proportional control. So in case of proportional control, it actually improves both transient and steady state. If you increase this value too much, the transient response is improved, but the steady state actually reduces it. But if you use the low value, then the steady state improves, but the transient dies out. So that is a compromise while you are using only the proportional gain. In case of, because I'm giving you some basic understanding of this, in case of you are using k plus ki upon s, it means you want to use pi control. Pi control means that this is the control. This actually, what does this control do? It actually reduces your steady state error. If there is some steady state error, it will try to improve the control action via integral control will be such that it will keep doing until you reach your desired steady state value. And similarly, in case of k plus kds, that is your PD control, this happens when your system has some errors, ripples. So in that case, when there is a rate of change, then this function performs in, and it improves your transient characteristics. So you can say this improves your steady state characteristics, this improves your transient characteristics, and k overall improve both characteristics. That is why in some cases we need to use PID. Now I'm going to switch on to the draft which I've prepared for your understanding. And what you will do at the end of this, you are going to write this program, develop this simulating model, and use a PID block, which I'm going to introduce you sooner or later. Then what you have to do, you have to just tune the values one by one and get your desired response. For example, any desired response of your kind. For example, in this case, let me share you here. Wait a minute, please. Yeah, in this case, you can see 0.05 is your final value, but you have to make it to the 1 because it is a unit step response. Similarly, you can increase the rise time, you can increase the settling time, and a lot of things. So whenever you can get at the end of the this section, you are going to get different KP, KD, and KI values, closed loop response, and with different rise times and overshoots and settling time, and you can conclude they plot all the simulated system with rise, settling time, and you can select which response is best for you. So remember, being a designer, you should have a confidence that which response is good for you. So now I'm going to give you a brief introduction of how the PID controller works. Before going into the details of these controllers, you have to understand some basic terminologies. How does an integrator work, and how does an differentiator work, and how does these work when they are working together with each other. For example, like I don't worry about it, I'm using a PID block here, but here I'm just putting the value k is equal to 1, so you can just consider it, as like this is simply a wire, and this summing point is doing nothing, so don't worry about it. So it is just simply a step input that is given to the integrator, and now we want to see what happens, the response against this step input. So we can see when you give a step input, and the integral response is simply a ramp. I'm going fastly one by one so that you can just get some idea, and at the end of this lecture you are able to understand how to tune your parameters to get the desired response of your wish. Okay, so now what happens when you give a step input to a 10 step size, it gives the same result, and again if you give a 100 step size, it gives again the same result. Okay, now go to the double integral. So double integrator means when you give a double integrator, automatically it becomes a parabolic function. So at a certain point, as you give an input, it gives you a parabolic function. You can, it means at ramp means, what does ramp mean? Ramp means that at every value, for example, if I go to this one, at every value at time t is equal to 2, it gives you 20 value. At time t is equal to 3, it gives you 30 value. Same is the case here. In parabolic case, at time t is equal to 2, it gives you the square of this value, 1 upon a square of this value. So you can get the square values at every time, 3 square values here, and then so in this case probably we were giving a step input, so it goes quite rough. So in a summary, you can remember, whenever you give a step input to a 1 upon s square, you give a parabolic kind of a response. Okay, now same is the case when you have increased the 10 step size, and then you again get it. Now we move on. Now what we have used, this is simply a wire. We are using a step input to a simple pole. Remember, in our lab 7 and in our single first order system, what we have learned, we saw, what we have seen, let me show you again here. We learned that, for example, if there is a, if you remember, I used a RC circuit, and the transfer function was a upon s plus a. So this is similar to this one, s plus 1. So it means if these two values are same, what happens if these two values are same, then the response will be something like this, and it will always reach its steady state value. Okay, but if I reduce this value or increase, so this value actually, what does this value do? This value actually creates a steady state error, and this value actually change the transient response characteristics. So in this case, what happens when I just give a step response, and 1 upon s plus 1, it shows that at one value it will reach the output. So I can see here at one value it is reaching the output. But one interesting thing is that when you make a feedback with 1 upon s, so what happens? It behaves similar to this block, similar to, like, if I'm using an integrator and I'm giving a feedback, it means that it will be working similar to the pole at s plus 1. I can easily show you. Look at here, please. Like, for example, if you're giving a feedback input 1 upon s here, and then you give, this is your r and this is your c, and you get a feedback here from plus to minus, then what happens? C upon r, in this case g upon 1 plus g, because this is a unity feedback, so h is equal to 1, and g is 1 upon s upon 1 plus 1 upon s. So where if you take more LCM 1 upon s, then it becomes s plus 1 upon s. SS cancel, and then we get s upon 1 plus s. So in this case, this function behaves similarly, like you are giving an input to a function with pole position at 1. So in this similarly, that is why both the output gives you the same results. Like if you are using a integrator with a feedback, or you are using a pole without a feedback, both gives you the similar results. So this is a very important conclusion here. Okay, so now what we are doing here, we are doing different values. I'm just trying to tell you how will you initiate the tuning, because in this lab you are not understanding an established method of PID tuning. You are just going to understand how the simple pole works, how the integrator works, differentiator works, so that you are able to tune the parameters of Kp, Kd, and Ki by yourself by understanding how these individual functions work. So in this case, because one is here and zero point 0.5 is here, it seems like that at when I give a step input to this value, remember I am again telling you, do not consider this. I'm not using a PID here. I'm just using a block. It is simply a wire. Okay, so when this is greater than, it means that this value will be overstepped. It will cross the step response. This value in this, it is understepped, and in this value it is moreover, so will be different. Let's see what happens. So in that case, when we have a point five value, then it gives a overstep. I already told you, overstep response. When we have another value point, yeah, like this value was smaller and this value was bigger, in that case it could not reach the other value, and it when it was 10 times, it reduced more. So it is very important that this a factor should be equal to this a factor in order to reach this value. That's how the controllers are usually designed. I'm just describing the phenomena here. So okay, again, so in that case, for example, if I try to draw a upon 1 plus a, for example, in this case, zero point 0.5 upon 1 s plus zero point 0.5, in this case zero point 0.5, that reaches something like this. It reaches to the desired value, and depending upon the transient response it got. So this is also another value in which s plus 2 upon s plus 2. This is the response of 2 upon s plus 2, and this is the response of 10 upon s plus 10. So you can see, cumulatively plotting these responses, we can see that, so that I have plotted these three responses. 0.5 upon s plus zero point 0.5, 2 upon s plus 2, 10 upon s plus 10. When you keep these values same, you always got to reach the desired step response. You can see that. But when you change these values, you got different results, something like this. So you can understand this phenomena very carefully here. So you can just make a block and understand how does it goes. So same is the case with the differentiator. Now I'm using a differentiator function of PID, because remember, ideal differentiator tells something very interesting. So you cannot sometime make a ideal differentiator. If you make a simulating block and you put s, it will always give infinity error to yourself. So because it, x2 minus x1 divided by t gives you d term, differentiator term, you can say s term. But usually this t is very small. If you put is almost very small t, because you want to take a very small change in x1 till x1 reaching towards x2, so it gives a very big a value. That is why it gives infinity. So in order to avoid that situation, I use a PID already built in function to use as a s. So this time I'm using, this is not a wire. This time this is a wire, but this is a simply differential function. So when you use a differential function, what happens, I'm going to magnify it and try to tell you. Now you can see what happens. This is your x1 position, and this is your x2 position. When x2 minus x1 divide by time, you get a very big response in order to reach that value. So that is how the differential works. That is why it always work when there is some changes in variable. If there is a constant line, you can see there is a constant line, it is not changing. Because I'm using some approximations, that is why there are some dips. Not dips, you can say kind of slight overshoot, but you can consider them equal to 0. Okay, So now let's go to the another response. Yeah, you can see another response with d is equal to 1 and d is equal to 10 will be making some difference. Here we are using kp is equal to 1, like is a unity, and we are having some different response, and let's see what happens. Okay, so now we are using, actually we are using a differential operator with s plus 1. I think you can skip this part because you can just consider these parts approximately equal to s. Like this in this part, actually your differentiator is dominant, s is dominant, and you are using a weak pole here. So with different weak pole, when the differential is dominant, you can see the response. When s is equal to, for example, when s is equal to -1, you see it is dying out very quickly, -20, and when s is equal to -5, it is dying out little faster, a little more slowly. And then when it is almost -1, then it is died out very slowly. So you can understand when you want to what kind of change you want to get when you apply a differential control here over here. Okay, so don't worry about it, we will be discussing these kind of things in your live interaction as well. So I want that you should have been asking a lot of questions when I'll be taking your live question answer, so that anything you are missing you can. So I plotted more and more response. What I did, this is very interesting. You remember, whenever we have a very big number s upon s plus 20 2000, then see it goes up and goes down quickly, with the green 20, with the red 2, with the blue 1, and you see we have a very small value 0.001, then it is almost not gonna change with the response, because so that is how it works. Now proportional integrator, in this case we are just learning the characteristics of PI controller, just by giving the step response. How does it work? Remember that I did not give any second order transfer function till now. I'm just teaching you how does these curve behave, so that you guys can get an idea how you have to tune your controller. So step response is there when you use kp is equal to 1, ki is equal to 1. Let's see what happens with different responses. This is very interesting. When you use different values of kp, for example, if I'm using kp is equal to zero point 0.5, so at till zero point 0.5 it will add some offset till zero point 0.5, and then kp is equal to 1 means at value 2, at value 1 it will give 1, at value 2 it will give 2, something like this, because it will increase with unity, because we started from there. So you can say at 1, at 2, it gives certain value, and at 3 it gives 2.5. Similarly here at kp is equal to 1, when kp is equal to 1 you have this offset, you see. So and when you have a kp is equal to 2 you have this offset. The summary is that whenever pi controller, let me actually I don't want to be much faster so that you just skip the concept. Let me tell you one thing. For example, you are having a kp is equal to 1 and ki is equal to 1. So what kind of response you are getting? Actually till 1 you will be having this, and then as soon as your 1 appear, you got this ramp value. But for example, if your kp is equal to 5, so you can say till 5 you are having this, and then you get this response. So in order to understand more clearly, what I did, I started from here. So till I'm again telling you this. For example, at one value, as you achieve the one offset, then you start ramp. Similarly, at 5 value, when you achieve the value 5, then you start ramp. So these kind of responses, it means whenever you use proportional control and integral control together, then the first proportional control is implemented, and later the integral control. Similarly, so you can try out different kind of phenomena, so you can understand. Now we see we are using the same value of kp, the same value, but we are using different values of ki. So when you use a different value of ki, for example, we are using a ki equal to, in case of blue we are using ki equal to ki equal to 1. So with the ratio of 1 it is increased. For example, At value 2 it will give you 2 answer, and at value 3 it will give you 3 answer. Similarly, if we talk about the red line, at value 1 it is 0, at value 2 it will be giving you around value of 4. It will be double. And in case of point 0.5, we can see there might be some pattern you can easily get with these values. So you can understand that how much I will increase the I, then how much effect it will be putting on my system. So that is why I have done these simulations for you, that for example, by changing the different values of ki, you will be having a different values of output. For example, with ki equal to zero point 0.5, at zero point 0.5, so it will be increasing. For example, at value 0 and 1 it will be giving you zero point 0.5, here at this value giving you 2, and then 2.5. Yeah, there you can see the phenomena: 1 1.5, 2 2.5, 3 3.5. So you can see the lower value of ki will make uh, um, the integral control trend towards the downside, and the higher value will be making it towards the upside near the 90-degree, and it will be towards the 0 degree. Okay. So similarly, the proportional differential characteristics. In the proportional differential characteristics, we have different characteristics. In this case, we have used this value of kp, and then with this we have used the similar value of d gain 111, with kp is equal to zero point 0.5 and 1, it gives you this response. The with kp is equal to 1 and it gives you this response, with kp is equal to 2 it gives you this response. So you see, with constant kp it gives you different error. So it means the kp offset remains in the system, it does not omit. But what happens next is the d action starts working, and then now we have probably different value of, now we are having a same value of proportional gain, but what we are having a different value of proportional. Now you can see the different magnitudes. For example, the red line gives the highest magnitude of adopting change. It means if you use a lower value it will remove more error. So guys, don't worry about it, you have to do this exercise one by one. I have actually went to the another level in order to understand you, teach you, just not by sticking to the lab. Just I try to make that whenever, because these type of control are very important for your future use. Now what we are doing here, we are actually using here probably let me see, we are, this is simply, you can go it by yourself. We are using a different value of proportional gain, and we are using a integral, same value of integral, so it gives a similar pattern. And then yeah, we are using a same value of proportional and then different value of integral. Now you can see with single order pole, you can see here, I can show you. Yeah, with this kind of, I remember I taught you two things. One is this differentiator. Pure differentiator have only s, and another thing is pole with differentiator with which have a solid s term divided by s plus something. So that gives you more smooth response. In the future you will be studying some lead lag compensators that are actually the start of these kind of topics, and these kind of specific theories that you are seeing in this curves are part of lead lag compensator. Now proportional integral derivative control. In the proportional integral derivative we are using different values, and we will be combining these phenomena, and what happens. For example, let's take blue line. In the blue line we are using kp is equal to 1, and then after taking kp the d action comes in, because it starts from 1 and d action comes in, and then finally with the d action it is also showing ramp. So you can conveniently guess what is going on. For example, in the green color it starts from around from 2, because there are some approximation that those are disturbed from here. It's not exactly starting from 2, probably due to these values, but you can say it is started from 2. 2 is the offset, that is kp gain, and then you have a some differentiator, and then that differentiator along with ramp kind, you get k is equal to 1. So you can easily now we are up to the second order system. that is actually belongs to our lab, which we have to do. So in the in the if we implement, I took this diagram from the website, and if you see that the proportional, integral, and derivative, they are all sum up and combined together to give the process plant, so that our plant can give us a desired value of the output. So you can see, I'll be not taking much of your time. And then now I just considered the underdam case, because this is the most toughest case. But later, probably in our example, there could be a overdam case. You can do it. Now what you have to do, you have to just use a KP and just to check. Remember one thing, one important thing. This is a your equation of underdam. So you see, in this equation, omega n and omega n square should be same. If these two things are not same, in that case, what will happen? What will happen? That your desired value will not be touched by the response. For example, if there is a 4, here should also be 4. If there is 16, here should also be 16. If there is 64, it should also be 64. And this is the underdam case. You can see all the point are zeta. In your lab 7, you can also use the transfer function something like this by mentioning zeta separately as a multiplier of the omega n. Okay, now we are going to see, yeah, you can see both the systems were second order. Zeta was same, but natural frequency was different. The higher the higher the frequency, the rise time will be faster. We already study in our lab 7 that omega d depend on omega n. If the value of omega d increases, which is in the denominator, the rise time is reduced. You can see omega n increase, rise time is reduced. So you can see this is the first response. Now you can tune around these values, so that you, which response you like. For example, you may like red response or blue, and you can tune it according to your wish, and you can find out the desired TSTR and TP overshoot and etc. Now what I'm doing here, in this response, we are actually using different gains as well with this. As soon as I changed kp1, kp2, and with certain different gains, what I found out that I am unable to reach the desired value. Now what we are doing in this and in the later diagram, probably this could be, yeah, now in this diagram we are using, no, in this diagram we have used lower values of gain, probably 0.5 or something, that which has given us this kind of response. I forgot to mention here, you can check it by yourself. But in this diagram we are using different value of p gain for different response. For example, the blue one we are using p is equal to 1. For red one we are using p is equal to 2. For green one we are using p is equal to 5. For violet one we are using p is equal to 10. So we can see different response. Until unless we are unable to match the numerator omega n with the denominator omega n, we will not be able to reach the desired response. So you have to do these things by yourself. There are some calculations I've done it. And case 4, when we are using a PI controller, in the PI controller what we are going to achieve, in the PI controller is trying its best to remove the steady state error. What I have done, I've used the same system, but this system was using only P controller. Whenever there was an error, it gives a fixed offset to be multiplied with the error and reach it to the response. And the final value was this. It was never going to reach the desired value of yellow line. But what happened when I used the I controller? I controller influence in such a way. I already told you in the start of my lecture that I controller helps in is removing the steady state error. So it has somehow removed the state error. And when you use PD controller, PID controller, then it not only removes the error, but it also tracks the it removes the ripple, like it shape up the condition monitoring. It actually signal conditioning to the response, and it finally reaches to the desired value. So these are the some basic plots which I have created for you. So what you have to do is to understand in this the lab is going to be very easy, because you have to put this plant and you have to select suitable value of kp and kd by hit and trial, so that you can get the desired value. But I never wanted that you do it just by hit and trial. So in order to make it more convincingly, what I wanted that you go through this draft I especially prepared for you guys, and so that you can have a better understanding. Remember, PID control theory itself is a, you can say, if I say control system theory is a branch of science where you can get a master's and a PhD degree. So PID controller understanding in the 30 minutes would be amazing, and it mean I must be a great teacher. Okay, so later now I'm going to discuss about something related to lab session 11. In the lab session 11, these unit has to be used. These units are available in the electrical department lab, feedback control lab. So we will not be able to do this, but what you can do, you can just simulate and do it as an open-ended problem. Don't use these things. What you have to do is to use a motor specification which you have learned in your undergrad course from your respective teachers, like the use a motor model, and just find the time domain specification. I might be discussing this with you, with your teachers, or your respective teacher might be discussing with you how to deal with the motor time constant, so you can easily find out the motor time constant. It is very easy. But okay, I can just spare one more minute to teach how will you find out the motor time constant. Motor response would be something like this. Transfer function of motor would be something like this. For example, omega n square upon s square plus 2 zeta omega n plus s plus omega n square, or you can say practically it could be point. So for example, 64 upon, for example, wait a minute, please. 64 upon 64 upon s square plus 8, for example, and 7 or s plus 64. And you can do one thing, time constant in second order system is also same, and it is usually equal to 1 upon sigma, and sigma is equal to 1 upon zeta omega n. So you can find out the value of zeta and omega n from this transfer function, and you can calculate the time constant and put this value in the lab 11, and you can calculate this. So I don't want that because of the corona and other stuff you are unable to do anything. We and other teachers have been trying our best to give you the online teaching. Hats off to all of them, and we are just trying our best to give you the best in this kind of circumstances. I hope you guys got a good knowledge. Anyhow, whenever if you have any problem, anything to ask, you can contact me anytime, whether you are from electronics department or electrical department. I have been your teacher, so we can discuss it, and you can also discuss this with your other teachers as well. Thank you very much. Hope you have a good session and exams. Stay safe. Thank you.